Hello, this is Myeong in Team Punchline from South Korea. In this time, I'll do presentation about client-side attack on live streaming services using grid computing. It was our project that we did for several months in 2020. We are the member of Best of the Best in South Korea. We are interested in offensive security and bug hunting. Grid computing is the method of using multiple computers. These are distributed but connected by networks to work together to accomplish a big task. Grid computing is called by different names depending on the type of resources it shares, and we focused on data grid. These services using data grid computing are widely used in platforms that provide P2P-based services. Among them, we analyzed the Korean services of 3 live streaming platforms, which were in high demand due to COVID-19. Live streaming services are also called internet broadcasting in general, and unlike TV, it is a service that allows anyone to broadcast their own content. Live streaming service platforms in Korea are using technology called grid computing to solve expensive network usage costs due to a large data throughput. Grid computing generally refers to a parallel distributed computing technology. In real-time streaming service, the service user computer is used to transmit data from a client to another client during the high-quality broadcast transmission process. The project was carried out on 3 target platforms in the following ways. First of all, the test environment was configured to avoid damage to other clients or servers, and later, the project was carried out through process execution flow analysis, data protocol analysis, and data modulation, code analysis, and crash analysis. These are hard things we got on analysis. Unlike general programs, it was difficult to analyze because various elements such as web browser, executable file, network packet were interrupted. In addition, there were anti-debug issues including Themida protector, but we could overcome it by using Themida for the hooking and writing automation code using memory dump. The core program used for grid computing was protected by Themida protector, so it was impossible to see the source code using Binary Ninja or IDA, where to solve this problem, we first unpacked this binary to a readable level using only debug script. Also, after bypassing the anti-debug techniques, the analysis was conducted through memory dump. And in the case of Mac, binaries protected in Windows are not protected by anything. The case of the Mac. So we could decompile it and then we could analyze more easily. Now, let me explain the behavioral structure of the binaries used for the grid. When watching a broadcast, the manager program that runs in the background or executed by a browser extension also executes the updater, and the updater checks the version of the local file before updating. After that, the updater runs another program for video data communication. It is called streamer. The streamer executed in this way first communicates with the main server and receives the IP and port number of the client it will connect to from the server. With this information, the streamer performs P2P communication and sends and receives video data. This data is passed to web browser and application, encoded and made available for watching. When a streamer sends and receives data through socket communication between clients, the relationship between the users is largely classified into two types as follows. The tree structure grid is in the form of a tree of data structure, and data is exchanged between clients. The mesh-based grid structure has a form in which the server transmits data to clients in a group, and then each other in the group send and receive video data. Company A and Company B are using tree-based structure, and Company C is using mesh-based grid structure. From this process structure, we want to suggest that attack surfaces. Although all three platforms are different, we are able to find a variety of vulnerabilities from a common attack surface. Through analysis of software of Company A, we could find vulnerability in three surfaces. Especially, request data is not applicable to Company A. Company A is using tree-based grid structure aside, and it doesn't need to transmit request data structurally, because it unilaterally transmits data from the parent node to the child node. As a result of analyzing Company B, we could find several vulnerabilities on two attack surfaces. And then last one, result of analyzing Company C, we found some vulnerabilities on 4 attack surfaces. Especially, we found a way to downgrade to the previous version of update file, including this, we found in all surfaces. Now, let me explain the attack surface we have suggested one by one. This is the first attack surface. It occurs while the user software, streamer file, communicates with the main server. A streamer file communicates with the main server, such as transmitting RAM availability or receiving peer list to be connected. This is also the first thing to do in the whole process. Information leakage occurs during this communication process. The analysis can be found in this table. Through packet analysis, we found only one vulnerability in Company C in this surface. In the case of Company C, the server transmits a private IP to establish a connection to clients in the same network. At this time, since private IP is transmitted even when not in the same network, unnecessary information is transmitted from the server. Since this is unnecessary information that can identify an individual, it is an information leakage. In fact, we could get a total of 70 IP information in 2 hours from a broadcast with about 2,000 views. Next attack surface is the communication section with the update server. All three platforms have the same flow of process, and they communicate with the update server using an update file. At this time, if the victim and the attacker are on the same network, attacker can use this attack surface. As a result of the analysis, vulnerabilities were found on 2 platforms. When one client wants to watch the broadcast, the update file is automatically executed to check whether or not it is updated. An attacker can force malicious code to execute by tampering with the update file through DNS spoofing. This slide shows the detail of update file tampering on Company A. Above figures are the code that update process executes another process. There are no verification routine before file execution as seen. So we could tamper the update file by DNS spoofing and remote code execution as root privilege.
에서 15년 버전의 모튼을 보는 것 같다. 그러면서 이제 이 공은 정말 잘 들어가면은 완전히 이건 뭐 장난이냐 뭐 이런 식의.
Next is company C. A right figure is the code that checks the file signature. Therefore, we can tamper a update file to arbitrary file, but we can still downgrade it to previous version of it, because previous version file also use valid file signature. If there are some vulnerabilities in older version of it, this vulnerability will be useful. Next is occurs in the process of communication between clients. In order to send and receive data between clients, various data is sent and received after socket connection establishment. The first of them, the initial data, will be explained. The initial data is for connection during peer-to-peer communication between clients. We could find 5 vulnerabilities about this space in all platforms. We analyze the initial data after the connection process. As a result, the stealing video, heap overflow, denial of service were found. In the case of company A, the initial data is authenticated after P2P connection at normal flow, and the video data is received. In this process, we noted that only the initial data is an authentication process that can receive video data. Found vulnerabilities that allow an attacker who is not participating in the channel to send initial data to the client in the channel, forcing the data to be hijacked. This is meaningful in that unauthorized data such as private channel, channel for an alert, and paid lecture that are not disclosed to people can also be stolen. It can also lead to personal information leakage in that it can collect certain people's watching history. We wrote that code using Python like that. Through this demo video, you can see the process of the video being hijacked. Like that. We could find the same vulnerability in company B. Data needs to be sent 3 times to be authenticated and for stealing video data. It initially transmits the channel ID given to the channel. It then receives the first sequence and the last sequence from the receiving client. If we send the sequence in between, we could receive the video data from that sequence. In addition, in company B, we could find heap overflow due to data length modulation. The response data for the initial data included the data length value. If the attacker receives the initial data from the victim and modulates the length value when responding, there is no routine for check about the length value, so it is passed as an argument of the memMove function and the heap buffer overflow occurs. Next is DOS vulnerability due to the initial data modulation in company C. In the case of company C, the ticket information is transmitted to check the client is normal user for service at the beginning of the connection. At this time, when the length header of the ticket is tampered, it is larger than the length defined in the ticket-related structure and proceeds to a different branch statement. Afterwards, the process was terminated with an error message, which allowed a denial of service attack. This is a denial of service attack at company C. Okay. Next surface is, likewise, it occurs in the process of communication between clients. Clients request other clients for necessary data, and this data is called request data. Company A is not applicable in this section because the video data is unilaterally passed to the child node. There is no need to request video data from other clients. In this section, we were only able to find vulnerabilities in company C. Basically, we could induce denial of service attack in Windows 10. The details of this attack will be explained in the next slide. When client receives a request packet, a streamer process parses the packet like this figure. It first parses the 1 byte data, which is the number of requests. Usually, the value of this field is 1. Then it parses the 4 bytes data, which is video sequence number. However, if we alter the request number field, it overlays the packet and the process terminates with the error message. Okay. This is victim's screen. You can see that it is connected with other clients, and this is attacker's screen. Like that, this vulnerability can cause a denial of service. Can you see it? Okay, next is about the video data. In this section, we could find many vulnerabilities for all platforms. We analyzed the video data, so we could find heap overflow that occurs in all environments except Android. We also found a pirate broadcasting vulnerability that could allow screen tampering and full control of other user screen. In the case of screen modulation and pirate broadcasting vulnerabilities, it is caused by weak data integrity verification. Heap overflow in company A. As a result of protocol analysis, there is a 16-byte header containing the data length in all video data. At this time, if the length value is altered and transmitted to clients, there is no routine for check the length value as shown in the code, and a heap overflow occurs in the main copy function. This vulnerability occurs in both Mac, Windows, and iOS. Next, in company A, we could find a vulnerability that could remotely change video of other clients. It is caused by weak data integrity verification. In usual case, client who wanna watch broadcast A, can you see? Can watch it because other client who is in higher hierarchy send it. And then see pirate broadcasting case. By hooking the send and receive function with Frida, the attacker could drop all the original video data and send the another video data to change the video and voice of other clients. Since the attacker can relay broadcast B, attacker can force the victim to watch any video attacker wants, like that. This video is about pirate broadcasting company A. The left screen is victim's screen, and right side is attacker's one. You can see the victim's screen is changed the one controlled it. Okay. Grid executable file of company B processes the video data received from other clients and sends it to the browser. When the dummy data with video data is sent, the receiving client sends it to the browser after processing the data. In this case, the video is stopped remotely because there is a problem with the process of sending data to the browser. Next vulnerability is picture distortion in company B. That picture is victim screen. The screen was mutated by attacker, thus we could know that does not verify the integrity of the video data. Company B is using tree-based structure, so we think it can be expanded to pirate broadcasting like company A. And in company B, based on analyzing data protocol and binary file, the sequence number is assigned to the first 8 bytes after header field. When the sequence number is processed, the value of signed long type is used as an index through the percent operation. Some part of the date can be tampered with by an attacker, so value used like index can be negative. This allows the process to access to arbitrary memory. An attacker could exploit this vulnerability to remotely terminate the victim's process. Next is picture distortion in company C. You can see the broken screen. That is victim's screen. That screen can be tampered with as shown in the picture when the video data is sent after hooking at the WSA send function using Themida. So we could know that does not verify the integrity of the video data, but company C only sends data about the requested data in mesh-based structure, so it will be hard to expand to pirate broadcasting. In this demo video, you can see the victim screen is broken by an attacker. Can you see? We found multiple vulnerabilities on 5 attack surfaces we suggest. You can see a table of the types of vulnerabilities summarized for each platforms. This is a description of the vulnerabilities found and how to patch and prevent these vulnerabilities. Structurally, grid computing in live streaming service is dangerous because the received data from other clients can be mutated. Therefore, from a security point of view, it is important to ensure the reliability and integrity of data sent and received between clients. In addition, in the case of tree-based structure, it is necessary to distribute the data flow because the parent node user can completely control the data flow of the child. Thank you for listening.